Okay, hello guys, welcome to the British Algorithmic Olympiad 2022 round 1 question 4. I've already made solutions to the previous 3 questions in this paper on the StudyWave YouTube channel. Definitely go check them out if you haven't seen them. Also definitely attempt this question and spend at least a few hours on it if you haven't done so yet. We've also got links to the GitHub repo that contains all of the code for this paper. We've also got a Discord community link where you can join and socialize with other people preparing for several kinds of Olympiads, including the algorithmic, informatics, maths, and physics. And with that being said, let's just jump straight into the question. So question 4, wolves. It's a snowy day on Mount Olympus. A new species of wolf have been occupying the surrounding areas. Researchers have named this species the lexicon wolf, L wolves for short. Okay, so this is just some waffly context. Okay, L wolves have a specific hunting style. They form a straight line next to each other at evenly spaced distances. For each wolf, they work out and organize a unique endpoint on a similar straight line several miles away so they can most efficiently hunt prey in the area. So I think in this paragraph, the only 2 words that are actually important here are unique endpoint. And this basically just means that every single wolf has their own endpoint. So basically they have a 1-to-1 mapping. So no 2 wolves can have the same endpoint. Every single wolf has their own endpoint. Okay. The L wolves are very stubborn, however, and will not change their direction having chosen a unique endpoint before the hunt. Okay, so this is just saying that once they've chosen, then they're not going to change it. Then, although research has shown them to be one of the smartest wolf species, whilst hunting they will kill anything they sense near them and will follow any tracks they pick up. As such, they cannot cross paths with another wolf during the hunt. Okay, so this is important. They cannot cross paths with another wolf. Okay. To overcome this, the wolves send out groups at different times where no paths overlap. We call one of these groups a pack order. Okay? So basically to make sure they don't overlap, they send out different groups so that the wolves in those groups never overlap. And L wolves are labeled from left to right alphabetically using uppercase letters and the endpoints similarly using lowercase letters. Okay, for example, if there are 4 wolves A, B, C, D, and their 4 chosen endpoints A, C, D, B, respectively, the possible pack orders are... Okay, and then it shows all the possible orders where none of the wolves would overlap going to those endpoints. A diagram of the pack order ABC is shown below. So you can see that if I were to write A, B, C, D, then you can see that A gets mapped to A, which makes sense over here. B gets mapped to C, which makes sense over here. C gets mapped to D, which again makes sense. And then obviously this can't be part of the pack order because then this would be overlapping paths. So we can't add this. But then again, D gets mapped to B, which also makes sense. Okay. And I think that we're not actually going to use letters for this because it's just easier to work with numbers. So I think we're probably just going to use a 0-based index here. And we're just going to say that instead of writing this, we're probably just going to say, 0, 1, 2, and 3. So instead of working with letters, we're going to work with numbers. So then 0 gets mapped to 0, 1 gets mapped to 2, 2 gets mapped to 3, and then 3 gets mapped to 1. So these 2 things over here are equal to each other. Okay, and now let's actually look at part A for 18 marks. So write a program that inputs the endpoints of W wolves where W is in between 1 and 27. So it's at least 2 and at most 26 because there are 26 letters in the alphabet, so that's okay. Where the first endpoint is for wolf A, the second for wolf B, etc. So yeah, this is basically just this diagram over here. Your program should output the number of possible pack orders followed by the maximum possible number of wolves in a single pack order. So, first of all, if we can answer, so we need to output two numbers here, but the most important thing is that if we can answer the first part, where we output the number of possible pack orders, then the second part should be very simple, because we just need to keep track of the counter, and then for every single connection that we're actually including in a pack order, then we can just increment the counter. So the second number here is not a problem at all. The main thing to focus on is the first number. Now, instantly, this problem should remind you of something. We have 4 items, which you can think of, well, W items in this case, and you should instantly think about subsets, because here we're basically trying to find all of the valid subsets. And in this case, a valid subset is where no two paths of wolves overlap. So now you should instantly be thinking, okay, so let's just use the typical subsets algorithm, where every single item in a subset can either be in the subset or not in the subset. So that means there's 2 to the n subsets. But also remember that a pack order has to have at least 1 wolf. Like, for example, here you can see that every single pack order has at least 1 wolf, because it wouldn't really make sense to have a pack order that has no wolves, because then again they said that this is not like extremely thorough, but somewhere they said that they're very efficient. So also, yeah, they're one of the smartest wolf species, yeah. So you can kind of safely assume that they're going to send out at least 1 wolf in a pack order. And then so yeah, there's 2 to the n subsets, but then that also counts the empty subset. So, because again, we could have that every single item in the subset is not included, and that would be a valid subset, but in this case it's not valid. So there are 2 to the n minus 1 subsets. And equally, if we were to have a mapping like A, B, C, D and A, B, C, D, then it's possible to have all of the wolves sent out at once, so that's not a problem. So now we just have to think about, okay, so in this algorithm, how are we actually going to filter through this? So again, remember that for a subset algorithm, every single item can either be in the subset or not in the subset. So for A there's 2 cases, then for B there's 2 cases, and so on. And then all of these have to be multiplied, because they, like, for every single situation where A is either in the subset or not in the subset, B can be in the subset or not in the subset, so that's why we multiply by 2, and this is 2 to the 4. So you can quickly see how this gets extended to 2 to the n, because in this case n is equal to 4. And now if we actually try and consider when a valid pack order is going to occur, this is the actual hard part. And I think that if you just knew the algorithm for computing subsets and you realized how to filter using this condition, then this problem should have been quite easy. So let's draw out, let me decrease the pen thickness. Let's draw out a example. A, B, C, D, A, B, C, D. And let's just say, for example, A gets mapped to B. Just for example. Now I want you to ask yourselves, for B, which possible endpoint mappings are valid? So obviously B to C and B to D is valid, but B to A is not valid. And yeah, this is a very obvious observation, but if you actually think about this very carefully, ask yourselves, why are these two valid? And the reason that they are valid is because C and D is in front of B. And since it's in front of B, that means we can place it, but then A is behind B, so we can't place it. So if we actually think about this, this means that if we keep track of the endpoint that we've already placed that is furthest to the right, so the endpoint that is furthest to the right, so for example, if we had the mappings a to lowercase b and b to lowercase c, then the furthest endpoint that has been placed, actually let's just say that a gets mapped to lowercase a. So just like in this example over here, the furthest endpoint that has been placed is lowercase c to the right. So that means that for c, the only situation where we could place c in a pack order would be if it gets placed, if its mapping is to lowercase d, because d is further right than c. So now using this observation, we can actually create a recursive algorithm to solve the question. And with that being said, let's go into the code. So I've got the code editor open here in part A. And yeah, the first step is just to input the endpoints. And then we're also going to set the max pack size. And again, this is very easy to keep track of, because if we can keep track of which connections are being placed in the pack order, then we can easily just increment some kind of local variable. And then once we get to the end of the recursion, then we can just compare that local variable to the global one and check which one is bigger. Do that for every single combination, and we'll get the second number that we need to output here. This is not an issue. Then destination indexes. Okay, so all I'm doing here is I'm remapping, like I said before. So A gets mapped to 0, B gets mapped to 1, and so on. So we're using a 0-based index here, and we're remapping the lowercase letters into numbers and putting them in the destination indexes vector. And then this is the actual interesting part. So the function calculate order, so let's just go to its definition. So obviously we're going to have to iterate through the destination indexes, so we pass this in by reference. Then this I represents the index of the current letter or the current endpoint that we're investigating in the destination indexes vector. So for example, on the first iteration, I is going to be equal to 0 because we're currently investigating the first endpoint. Then it goes to 2, then to 3, and so on. And then previously used index, this is the index that is furthest to the right that we've currently placed. So out of the endpoints that we are allowed to place, previously used endpoints is the one that is furthest to the right that we have already placed. And then pack size, this is just checking how many wolves are in our current pack size. And then max pack size, this is just the global variable that I explained here before on line 62. Okay, so let's actually jump into the recursion. So this is our base case over here, which is when we get to the end of the destination indexes vector. And then at that point, we want to actually compare our pack size with the max pack size. And if our local max pack size is bigger than the global one, then we want to update it. And then when we actually get to the end of the destination indexes vector, then we want to return 1, because that means we have found one possible pack order. And then over here, I've just set up a variable to say total pack orders, which is just saying the total amount of pack orders currently. And if destination indexes I is greater than previously used indexes, then this means that the current endpoint that we're investigating is further to the right than the current endpoint that is furthest to the right. So this is the crucial condition that is needed to make sure that a connection between a wolf and an endpoint can be in a pack order. So this is the thing that actually ensures that a pack order is valid. And if the current endpoint is further to the right than the currently rightmost endpoint, then we can, obviously we're going to increment I, But then most importantly, we're going to include it in our pack size. So we're going to increase our pack size by 1. So this is the thing that actually counts the pack size. And then also remember that we can always not include a connection. It's very easy to not include a connection. Not including a connection is not a problem. So on line 54, this is the case where there is no connection included. So we're investigating the current endpoint, and this endpoint is not going to be included in our pack order. So this is not an issue. We only get an issue when we try to add something to the pack order, which is on line 52. And then we just return the total pack orders, which is just the sum of the possible pack orders where we either include the endpoint or not include the endpoint. And again, knowing the typical subsets algorithm is very, very useful here. If you don't know that algorithm, definitely go check it out and then come back. This will make a lot more sense. And this is basically the entire algorithm. And once we do that, then we're going to get the total pack orders, and we're also going to get the total max size, because we're at the end of our recursion, we're checking for the total pack size. And then we're just outputting the required numbers. And then again here, remember, -1, because we need at least one pack order. Whereas this is going to be calculating the pack orders including the empty pack order, whereas an empty pack order is not valid, which is why we -1 over here. And now, yeah, that's everything for part A. Let's move on to part B. Okay, part B for 2 marks. Suppose a pack of 8 wolves chose the endpoints A, B, C, D, E, F, G, H in some order. What is the average of the maximal number of wolves that can hunt over all permutations of these endpoints? Give your answer to 2 decimal places. Now again, this is only 2 marks, so personally, especially if you're doing this in C++, like, this might have not even been worth the time, because looking at the code is probably quite a lot to implement for only 2 marks. It's not difficult, but it's just slightly annoying to only get 2 marks for this. But here there's nothing special going on. You literally pretty much just a brute force approach. Go over all of the permutations and then just use the same algorithm from part A. So again, just going straight to the code editor. For part B, just getting the typical endpoint in sorted alphabetical order. Then I'm just converting these to numbers. So A gets put to 0, B gets put to 1, etc. I didn't even actually have to do this, but I'm just that lazy that I can't be bothered to put it into array manually. It's just quicker to type this. And then total, this is the total of all of the maximum pack sizes for every single permutation. And this variable tracks how many permutations there are. We don't actually need to track this, but it's just like, we could alternatively just calculate how many letters are there. 8, we could just do 8 factorial. But again, this is just very simple to plus equals 1 every single time. So then we're going to do a do while loop, which is, we're going to make use of the next permutation function in C++. And this is basically just going to call the previous recursive function from part A. It's going to get the max pack size. It's going to add that to the total, increment the permutations variable, and then max pack size is equal to 0. This needs to be reset, because remember, for every single permutation we need to find the max pack size, so we need to reset the max pack size to 0 so we can accurately determine the next max pack size. Gosh, that is a lot of max pack sizes in one sentence. And yeah, that's pretty much it. And if we were to run this, then we would have, will this work? A.out? No? Okay. Maybe compile. Yeah, and then we get 3.77, which is correct to 2 decimal places. And yeah, that's really it for part B. Okay, question C for 5 marks. The wolves in part B are trying to remember which permutation of A, B, C, D, E, F, G, H they originally agreed upon. To keep their hunting strategy secret, they speak in some sort of code. The following is said. I'm not actually going to bark in a YouTube video, but just read these and you'll understand. And then suggest and explain an original list of endpoints. So I'm going to be honest here. I feel like you could have said any kind of waffle in this question and you probably would have picked up like 2 marks. Definitely you could have picked up 2 marks here. To get the full 5 marks, you would have to say some pretty high quality waffle here. And I'm going to go through an example of that. And if we actually look in the mark scheme, there's an example. And I don't think I actually got the exact same answer, but I had the exact same logic when I was doing my one, so converting it to binary and then using the subscript to plus and minus depending on what the subscript is. So yeah, go ahead and read this. Pause the video if you want. So I'm doing pretty much the same approach. Okay, let's actually jump right into it. So let's actually write down the wolves and what they're barking about. So F, G, H. And I'm not actually going to go through much detail with how binary works and how adding it. I'm kind of just going to assume you already know that. And if you don't, then just go on any YouTube video. There's plenty where you can learn it. Then, okay, for A, we have 0, 0, 0, 1, which is just a 1. That's simple. And we have a 0, 1, 0, 1 plus the 1 in the subscript. So that's 1 plus 4, that's 5 plus 1, that's 6. And then we have 4 plus 1, which is 5. Then for C, we just have 8. Then we have 0 plus 2 in the subscript, so that's just 2. And then we have 1 plus 2 plus 4, which is 7. And then for E, we have 1 plus 2, which is 3, and then plus 1, which is a 4. And then we have a 4, and then, okay, this is very sneaky. This is actually a minus 2. I actually barely noticed that. Okay, so then we have 4 minus 2, which is just 2. And then we have 1 plus 2, which is just 3. And then we have 0 plus 1 in the subscript, which is just 1. And then we have 1 plus 4, which is 5. And then for G, we have 1 plus 2 plus 4, which is 7. Then we have 2 plus 4, which is 6. And then we have 1. And then again, this is quite sneaky, but this is actually a minus 1, if you didn't notice. And then we have 1 plus 2, which is 3, minus 1, which is 2. Now, I think I'm not actually going to write this out in whole sentences, but you should in the exam. But the general strategy is that if there's only one option for a letter, then they should get priority for that option. Because we could say like F is like the kind of wolf that is like so chilled out, like he doesn't care which number he gets. He can get a 2, a 3, or 1. And then the ones that have only one option, these wolves are the stubborn ones. These are the ones that literally can't reason with them at all, and they're saying, oh, I only want this one. And again, I could go ahead and convert these to letters, but it really doesn't matter. We can do that at the end. So again, we can just say, we can write out A, B, C, D, E, F, G, H. We can put these in columns as well, just to make it slightly better. And then we can say, okay, so A only goes to 1, so we can just say that's a 1. That's done. And then again, C goes to 8, so that's again not debatable. E goes to 4, not debatable. H goes to 2, not debatable. And then we can go ahead and cross out all of the numbers that have already been used. So 1 has been used, so we cross out this one and this one. 8 has been used, but no one wants 8, so okay. And then E, a 4 has been used. No one cares about 4 either, okay. And then 2 has also been used by H, so then F can't use the 2. Okay. And then also D can't use the 2. So now looking again, D had 2 options before, but now only has 1. So now D is a 7. So we cross out D, and we cross out the 7. And we've just used the 7, so now G can't have the 7. And what else can we say? Now G only has 1 option, so now G has to be the 6. So then we put 6 here. 6 can't be used. B can't use 6 now. And now this is done. So now B only has 1 option. So then B is a 5. And then we cross out B. And we can't use a 5. And that means F can't use the 5. But now F only has 1 option, which is 3. So then this is 3. And now we can check, does this actually work? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, it does work. Very nice. Can I actually get rid of these? Got some high level precision. Okay, done. And if we actually go ahead and convert these to letters, so we have A is equal to 1, B is equal to 2, C is equal to 3, D is equal to 4, E is equal to 5, A, B, C, D, E, F, G, H equal to 6, 7, 8. So if we actually convert these to letters now, we can say A1 is equal to A, then 5 is equal to E, then 8 is equal to H, then 7 is equal to G, then 4 is equal to D, 3 is equal to C, 6 is equal to F, and 2 is equal to B. So our final answer is G, D, C, F, B. And is this the same as the example? We have like A, C, H, G, A, C, H, G. Oh no, it's slightly different. But then again, as long as it's consistent, I don't think it actually matters too much. Oh no, it is the same. I just misread this as a C. This is a E. Okay, let's check again. A, E, H, G. A, E, H, G. And then D, C, F, B. Oops, this is the previous. D, C, F, B. Oh, okay, so it is actually the same. Okay, so that's nice. And yeah, that's everything for part C. And that's actually the end of the entire paper. I hope my solutions helped you at least a little bit. If they didn't, then feel free to comment on any of the videos. I'll try and respond. And you could also join the Discord community, where you can talk to me on Discord. I can help you out with the questions if you want. It's down below in the description. And yeah, I guess I'll see you next time.